So we got this set up. This is number 7 on the packet. Suleiman Nanush, 2.45 meters, throws a basketball horizontally at the top of his head. We are given the final velocity here, but that's a vector. And we're asked to find the speed with which it's thrown. Well, if we break down that final velocity into its components, we can find the Vfy and we can find the Vfx. Oh, okay. Who cares? Well, because Vfx is equal to Vi on the x, and that's what we want, because there was no acceleration on the x. So, at the heart of it, and what Grant picked up is they put this into Pythagoras. Okay, great. So Vf squared is equal to the square root of Vfx squared plus Vfy squared. Oops. Let me get rid of that square root. Yeah. Try this. Vfy squared plus Vfx squared. There, no square root. We're not solving for Vf. We're given that. Okay, so, well, that's good. We have this and we want this. What we need to do is create some kind of expression that will get us this. So, based on what you know, Vy, let's see, Vyi is 0, and we know delta y, which is 2.45 meters. So we've got acceleration, initial velocity, and delta y. From that, can we create an expression that will solve for this? Let's copy some stuff and play around with it on the next page. Okay, so we've redrawn this. We've taken all the things that we knew from the last page. We've got our drawing in miniature, and we've established this relationship that if we want to solve for the final x velocity, we can take the final velocity squared minus the y final velocity squared, subtract them, and take the square root. Okay, good. Now we just need to get an expression for this so we have something to substitute. And we've got this old standby. Nope, that's not it. So we're trying to link acceleration, delta y, and the displacement and final. So Vi, Vf. Okay, perfect. Vf squared equals Vi squared plus 2a delta y. Hey, looky there. There we go. So back to the 4 goldens. Of course, V, and these are both on the y-axis. Viy was what? It was 0, so that goes away. So Vfy squared is equal to 2a delta y. Well, right there, we can plug this in for that. So, let's copy what we can here. Okay, we'll copy this, paste that. Okay, so we've got the square root of the final velocity squared minus 2a delta y equals Vfx, which is also equal to Vix. So we can say that. Okay. Plug 9.7944371997 meters per second is your initial x velocity. So this is a good example of having a problem where you've got a bunch of pieces of information and you just have to kind of keep creating expressions. That's the process I was kind of starting with you yesterday, Grant, where like I'm going to play with this every single way I can and create a bunch of expressions, because one of them is going to be something that I can plug in. And that's, honestly, fighting with it like that is superior in terms of learning to problem solve than going, okay, this is what I do. I use this equation. I plug this in. Like, really having to struggle with it engages different parts of your brain. So that's it. And when it sig figs out, what do we get? 3.97 or 9.97? Oh, it's 2 sig figs. Okay, so 9.8 meters per second. No, it should be 3 sig figs. Yeah, the book sig figs are wrong as usual. Yeah, it would be 9.79.
Why are we running velocity
Because there's no acceleration on the x-axis. Therefore, whatever initial velocity it has on the x-axis is the same as the final velocity on the x-axis. On number 8, when it says you're going to jump horizontally, it says horizontally, so that's your Vx. And of course, Vx initial is going to be the same as Vx final. Now, if we do our old standard of the x and the y, you have a Vxi, you have a Vxf. You have a Vyi, which is 0. You have acceleration on the y, you have delta y. So can you figure out Vf on the y? Or can you create an expression for Vf on the y?
So wait, for the x side, the velocity.
Yeah, those are equal. And basically, again, we're looking at that final sort of triangle. Where we have Vf, Vfx, and Vfy. So that's just Pythagoras again. That's all that is. That we have Vf squared equals, whoops, Vfy squared plus Vfx squared. It is a little bit simpler. It's actually, it's about the same, really, because if you're going to have to create an expression for that, and then you have to find that.
I was thinking we had 2 of them.
So no, you don't. But you've got enough information on the y-axis to create an expression for your final y velocity using the 4 golden equations. I think I may have forgotten to hit the record button on all of this, but we've laid a lot of stuff out here. So you've got an initial x velocity, which is, of course, equal to the final x velocity. We've got an initial y velocity of 0. You've got acceleration and the displacement on the y. So you've got enough with that with these 4 things, to build an expression for Vfy that you can plug into there. So this is what you're substituting in for. This is your overall objective, and I'm going to do this in red.
Okay.
Sorry.
Does Vf equal Vfy then?
Does Vf equal Vfy? No. Vf is a vector. Vf is a vector, and if we were to draw the final little triangle, Vf is comprised of some portion Vfy, some portion Vfx.
But if what's Vxi and Vx?
They're equal to one another.
The initial and the final.
Yeah, this is Vxi, and the velocity on the x-axis doesn't change because there's no acceleration.
Wouldn't it get less?
No. Not unless we're counting wind resistance, which we don't.
Okay.
In the real world, would it diminish ever so slightly? Yeah, but there's no force acting on it on the x until it contacts something else, and a force of friction would act on it. Air resistance is nothing more than friction from the air, and we disregard that because it's fairly minimal. But no, the velocity on the x-axis doesn't change because there's no acceleration, or none that we're going to talk about. There is some minor acceleration due to wind, but that's it. It's important.
Okay.
You're not solving for Vfy. You're creating an expression for Vfy that you can plug into this equation.
Are we always going to use this equation?
Well, in a case where it's warranted,
Are you supposed to find the degree for that?
you don't need to. Does it ask for the degree?
It gives you an answer, but then it gives you. No, there's another answer.
There's like two. It's 6.88.
Oh, okay. Hold on. Let's.
You want-
The question doesn't ask for. The question doesn't ask for the angle that you land at, but you can figure it out. You don't have to square that because it's already equal to VF squared. So that just plugs in.
See, like, when you fix it, it ends up going like this. Square root.
So VF equals square root of.
So are we only finding VF, or do we need to find that?
It doesn't ask you for the angle, so I don't think you need to find it.
Okay, so our answer is 6.88.
Right.
Well, I don't know why they have to check.
I'll look at it and see if I can figure it out. Meters per second, 6.874518165 meters per second.
Make gravity negative.
Your book does this whole bizarre thing where when you start doing problems that are on the y-axis, they change acceleration to g, and they give g as just the magnitude of acceleration due to gravity, negative 9.81, and then they use negative g.
I feel like that's so confusing.
I find it so counterintuitive and so confusing, and I've found it much easier for me and for students to just keep using acceleration, and you know that when it's acceleration due to gravity, it's negative 9.81 meters per second squared. And all of my physics students have done very well with that. And I find the way the book handles that one, I like this book. I think it's a good layout. I think it's got a good progression. I think it's got good problems. But I find that one thing that they do really unhelpful. And we had that discussion in chapter 2 when we started doing free fall problems, and I said, look, here's how your book handles it. I don't like it, and I typically haven't taught it that way, but be aware that that's what you're seeing in the book and in the book problems. So yeah, that's their thing. So then yeah, VF is 6.9. 6.9? No, 6.87. You've got 3 sig figs, right?
No, it's 3.0.
Oh, 3.0. You're right. Okay, so 6.9 meters per second. Okay. Okay, this is just a picture of how happy physics makes you. So that's it for the day.